To everyone present here. I'm Aham and I'll be here presenting on cross-spherical gears and cross-spherical gears. They are a very complex form of gears. So before we move into cross-spherical gears, we'll start from the basics. What's a gear? So mechanical engineers, any simple answer, one word. What's a gear? Anybody? Okay, it's fine, leave. So what's a gear? A gear is simply a wheel, but it has teeth. Now why would you say you've added teeth to wheels? Wheels can move on their own, right? But no. The property of gears is that it's used to transfer motion from one part to another. And that main element which transfers motion from one part to another is those teeth, because they mesh together and then they transmit force to one another and it moves. That's what drives one component and gear, and it drives another component. Next. Kritik. Next. Okay. So let me take you on a time travel on how our ancestors used gear back in 200 BC. So back then you might have thought that gear they're probably used for like what? Nowadays they're mainly used in transportation. But back then it was used for way more important things. Like we had the anti-vector mechanism. Now just saying it's from a ruin and it was found in an island which has its name anti-vector. So what this mechanism used to do was it was like a calendar. Now a calendar which would predict the year cycle based on just visible astronomical objects. Now back in those days we could only see three astronomical objects, which is the sun, the moon, and the bright planets like you have Venus, Mars, and sometimes Jupiter, depending on the cycle. So what you could do is you could just turn the three visible planets, and then you would get an estimate of what other constellations there are. So it would give a live calendar like a compass, but for years. So that was anti-vector mechanism is for. Now we have the south pointing chariot. This was used in China in around 100 BC. What this chariot would do is basically, because back in those days they didn't have compass, they didn't have the idea of magnetism and all that. So what this would do is, the wheels are attached to a certain kind of gear. Now every rotation which the wheel takes, say it takes a left, the south pointing chariot, like it's a pointing statue, right? So it'll adjust it to, keep pointing at the south. So no matter how far the traveler just moves, say I go left, I go right, I go anywhere, the pointer is always pointing at south. And that was very efficient in navigation. And then we came to mechanical clocks, which was used to just maintain a good sense of time, and this was happening in 15th century. Next. Then Leonardo da Vinci. We all know about him, how innovative his codices were, and he also proposed gear transmission systems, and then those are still being referred today for future developments of gears and all. Then in the first industrial revolution, we have textile mills. Textile mills simply they totally took the work from crafted artisans and put it into unskilled artisans. Anybody could operate textile mills and they could go any fabric yarn, and then they could totally sell it to people, because back when only crafted artisans could make those decorated designs. But then textile mills, you could automate that. You could make a machine with gears, work and make it for you. So any unskilled person in a textile mill, they could sell clothes. So that was the first industrial revolution. Second industrial revolution, that happened with steam engines. Now this was the first thing which, you could move a metallic object or a heavy vehicle simply based on power. And that's what steam engines was for. Next. Now coming to a bit more ahead, like 19th century, 20th century, we have automobile gearbox. We got car bends, cars, and then they had manual transmission system. Now we have DCT, dual clutch transmission, we have CVT, continuous variable transmission, and various other complex for easifying our daily commute travel. Now other application is in power tools. We have drilling tools, we have various other saws, and all of those are totally given by gears. Now also in household tools, we have washing machines driven by gears again. We have blenders again driven by gears. Next. Now current developments are mainly energy harnessing systems. Energy harnessing system, you can see a windmill over there. What that does is basically the force of wind pushes the wind place, and then that motion is taken by the gears and is taken to a dynamo and it creates energy. It's the simple process of electric generator. And then we have the robots. Robots, the failure, they just got introduced in 1960s, and what they do is they basically take up a specific task and totally automate it. They are built for one specific task, but then now they're growing up to be multifunctional. You can like you have the Tesla robot, right? You can make it do various amount of tasks and it keep upgrading itself because the company is continuously improving all the algorithms and the processors. Next. Now, we saw all the applications of gears, but then what basic kinds of gears there are? Those are types of gears. So you have a very simple one, which is called the spur gear. No complexity, it's just straight tails, that's all. And when this we use is when you're transferring, force from two parallel shafts. One parallel shaft is right parallel to another, so you can put a gear and then it simply move and transfer force. And then you have a helical gear. Now this has a bit angled teeth, very much like spur, but then it just has a teeth angled a bit. Now what that does is it gives more, meshing. Now when you have more meshing, the gear can transfer power more efficiently, right? So it's used in high torque machinery and automotives. Next. Now we have a bevel gear. Bevel gear, there's a recent development of other gears, so they're angled in a conical way. Where these are used in current automobile systems where central rod is, it is taking the power from the engine and then diverting it to the wheels. So you can see one is perpendicular and then there is the other one like that. The main thing drives the other one, and then this is helpful when the shafts are totally, not in parallel or angled. These are, different angles. Now we have a worm gear. Now these are used in, elevators, hoists. Just by, you can move the worm gear, and then the worm is basically this. You can see that cylindrical rod, right? So you just have to move it, and the gear will turn, and then the gear will be attached to a pulley system, and then that will just lift the hoist and then elevators. But the unique thing about this is the gear, if it rotates, it cannot turn the worm gear. So it's used in very control specific applications. Next. Now, what are the performance bottlenecks of these gears which I just discussed? So in this spur gear, you have parallel shafts, and they're very noisy at high speeds. In helical, they generate axial thrust because of the angling, and which needs another support to balance that axial support. Now we have bevel gears which are restricted to single axis angle. Like you saw the conical thing, right? So it's at a specific angle. They customize the angle depending on the customization of the job they need to do. And the worm gear parallel shafts, and they are very noisy at high speeds. Now these are performance bottlenecks of the current existing gears. Now I've introduced to you what cross-spherical gears are and how they cover over these bottlenecks. So this is a cross-spherical gear. It's a 3D model. So next. The specialty of these gears are that they have 3 RDOF. So any mechanical student would know what RDOF is anyway. But to the non-technical students, I'll say it's rotational degree of freedom. Now when I say degree of freedom, it's basically how many ways can an object move in. So you have this door, right? How many ways do you think this door can move? Just one. It can just move like this. So it just has one rotational degree of freedom. Nothing more than that. It just move like this. But now if I have my hand over here, it can move like this, this. I can even bring it like this. This is 3 degree of freedom. And then no gear, no ball joint can totally, replicate this. No gears. The current robotics arms are based on single gears which are driven in x-axis, y-axis and z-axis. Say the robot has to get an object over here. What it has to do is first it has to adjust its x-axis like this, then the y-axis and then the z-axis to get to the point. But then what this RDO gear can do is it can directly reach for it. Because it has 3 degree of rotation freedom. That's this is our arms. And wait, back. Yeah, those 3 degrees of freedom, as you can see in this animation, is the first one is roll, where it rolls on this axis like this. Then you have pitch, which rolls like this or this, and then you have the yaw, which rolls like this or this. Yeah, this is how a cross-spherical gear is made, very simple to understand. So you have a basic square gear and then you pad it, it turns into this. Now to drive a spherical gear, you need a different kind of gear. So by hopping, you can totally make a driving gear. Now this driving gear, because one driving gear can only give you 2 degrees of freedom, you can only rotate and then do this, pitching and rolling. So to totally utilize the 3 degrees of freedom that the cross-spherical gear has, we will add another driving gear. And this is how you hop it. So another structural axis and then you hop it. So it gives the totally 3D of freedom. And then you use the second driving gear and that's how it works. And the part which you see over there is basically meant for the output links to be attached. And you can just make it revolve in any direction you want. You don't have to set it in x-axis, y-axis and then z-axis. Just directly because it has 360 degrees of rotation freedom. Now I just mentioned few performance bottlenecks, right? Now this is what CSC does. CSC in short, cross-spherical gears. So square gears, they have parallel shafts and obviously high speeds. Now these, if you replace them with CSC, they provide pointer and they have multi-axis functionality, like just as I said, X, Y, Z. You don't need all that. They can just directly go into that. And we have helical, which generate axes and like I said. Here, there is no axial thrust, and that's why it gives you more durability. Now, bevel gears, same, they are restricted to single axis point, but CSC is flexible and it has reduced alignment issues because this is sphere. You can align the output link wherever you want, and it will be fixed over there. Now, with the worm gear, it was inefficient due to sliding friction and heat, but CSC it uses rolling contact for higher efficiency and durability. Okay, now what are the applications of these gears? Like where and what can be used? We have in different fields, robotics, compact multi-axis control, like I just said. The current robotics arms are, single gears, one has to move in X, Y, and then Z. This multi-axis control all at once. It just directly go for the object, just directly execute a task, making the robots functioning very effective. Now it has high load bearing capacity and very high precision because it has so much of an area to work on. It has a very high work volume. So you can totally directly control where you want it to be there. And it's used in computer vision. You have the Tesla's watt, right? So it has a camera. And then it moves its arm in respect to, grab that object. But then those algorithms are very complicated because they have to move their x-axis first, y-axis, and then z-axis. Here you can just directly locate it and then just use the RDF freedom with cross-spherical gear to provide. And in medical, so like I said, this ball and socket joint is what cross-spherical gear are. You see our shoulders, right? They can move anywhere you want. This, I can rotate it like this. I can rotate it like this also. Anyway, yes. It's a ball socket joint. Now that's what in medical you can do. You can create prosthetic limbs which are not limited to XYZ. You can create a more natural version of your own arm. Okay. And exoskeletons are meant for people who have paralysis, so they attach it on the back to give them the spinal support which they lost. And tight space dexterity. There are multiple medical probes which are inserted through small holes, and then those things need to be manipulated very carefully. If there's even a 1 mm miscalibration, it could injure your critical organs. So the 3D of gear, because it's not limited in 3 axes, it can just directly go with this 360 degree of freedom. It has this dexterity. Now in aerospace, satellite joints. Satellite joints because, again I said, it's a simple thing. 3 axis versus just 1 RDO. And then lower cameras. Now why I'm saying lower cameras is because the current cameras which are used is just flat, square. And then whatever you see is directly like your phone. But then what if you could move this camera like our eyes do? Our eyes never just look like this. You can look like here, you can look here, you can look there, you can look wherever you want. And that actuation for the camera can be given by cross-spherical gears. You can insert it right behind the camera lenses and then it could move and then sense its surrounding and it can get its depth very efficiently. And then multi-directional stabilization. That's the challenges, cost and manufacturing. Of course, this is a very complex area. It's not a simple gear which you can just part from. You have the rotational parting. So it has its manufacturing complexity, but then it stands for its benefits. Like you want to make your robot more efficient, more faster, next level, because the future is all about innovation. How you improve already existing systems. So that's what this challenge is called, and then challenges are meant to be overcome. They're not, you cannot see them as a disadvantage, because every single system which is there in the world, it has a disadvantage. Every fan, every AC, even the project has its disadvantage, but you have to use them within the limit and overcome that challenge. Now, compatibility issues with existing systems. For the entire 20 centuries, since the first use of gear, we've just been using, square gears, just, circles. And they've been totally incorporated in our system. But this is a 3D gear. This is totally groundbreaking, and the systems will need to think in a way different way to, bring the compatibility. So we have potential challenges in maintenance and repairs. This can be overcome by using the right material, which has, good durability, good strength, so it doesn't, go through wear and tear upon repeated usage. And of course, like any material which is there in mechanical, it of course has to go through wear and tear because it's being used. So you have to replace it within a fixed period of time. Advantages, like I said, so you have improved precision, you have reduced maintenance and enhanced durability, then compact, space-efficient design, because you don't need to give 3 axis controllers. You can just give one and it's totally directed. And you have potential for advanced robotics and prosthetics, like I mentioned, medical. And then we have enhanced fluidity of motion and lower requirements due to single integrated control. You don't have to manage 3 different axis controls. You can just go for single, which just manages the total rotation. Quick next. Open for Q&A now.
Can you just tell me how you can maintain it?
How can I make it? Yeah. So